You know, right at this very moment, you're experiencing a wave. Actually, you're experiencing a whole bunch of them. The light coming from the screen to your eyes, the sound of my voice. Yep, they're all waves. So in this explainer, we're going to break down exactly what that means. And that is no exaggeration at all. I mean, the light you're using to see this screen, that's a wave. The sound you're hearing, also a wave. And of course, you've got the classic ocean wave. They are, quite literally, everywhere. It seems like such a simple question, doesn't it? But the answer connects everything, from a surfer catching a break in the ocean all the way to the radio signal in your car. So what's the one fundamental thing that ties them all together? Well, it's this. At its absolute core, every single wave, no matter what kind it is or what it looks like, is just energy on the move. It's a way for energy to get from point A to point B, usually without moving the actual stuff in between. And this quote from a surfer just nails it perfectly. Think about it. A surfer isn't riding a block of water that came all the way from the middle of the ocean. Nope. The water itself is mostly just bobbing up and down. What they're really riding is the energy that's traveling through the water. Okay, so all waves move energy. But it turns out there are two fundamentally different ways that get that job done. So let's break down those two types. On one side, we have transverse waves. For these, I want you to think up and down motion that causes a sideways effect. The vibration, the wiggle, is at a right angle to the direction the energy is actually going. And on the other side, we have longitudinal waves. For these, think push and pull. The vibration is moving back and forth in the exact same direction that the energy is traveling. You know, the perfect way to picture a transverse wave is a Mexican wave in a giant stadium, right? Each person just stands up and sits back down. They don't go running along the aisle. But the wave itself, that awesome pulse of energy, travels sideways all the way around the stadium, completely perpendicular to the up and down motion of the people. Now, for a longitudinal wave, imagine a conga line where people start pushing the person in front of them. Each person just shuffles forward and back a tiny bit, right? But that push, that little squeeze or compression, travels all the way down the line. The movement of the people and the movement of the energy are going in the same direction. This is why it's often called a pressure wave. All right, let's zoom in on that first type. And we're going to use the most famous example out there, the ocean wave, to really understand the anatomy of a transverse wave. But hey, this isn't just about water. Light, radio signals, microwaves, all of those invisible things flying around us travel as transverse waves. It's the same basic up and down motion you'd see if you shook a long rope. It's just happening on an electromagnetic level you can't see. And the anatomy of these waves is super simple. The highest point the wave reaches, that's called the peak, or sometimes the crest. The lowest point it dips down to, we call that the trough. The whole wave is just this repeating pattern of peaks and troughs. So, how do we actually measure these things? Well, we mainly look at two key features. First up is amplitude. That's all about the wave's power or intensity, basically how high a peak gets from the middle resting position. Think a tiny ripple versus a giant tsunami. And second, we have wavelength. That's just the distance from one peak to the very next peak. So, in simple terms, amplitude is its height and wavelength is its length. Okay, time to switch gears and dive into our second type of wave. And for this one, our go-to example is going to be the sound wave. Sound is the absolute classic example here. But you also see this with certain seismic waves from earthquakes. Honestly, the best way to see it for yourself is to take a slinky, stretch it out, and give one end a good push. That pulse that travels forward and back, that's a perfect longitudinal wave. So instead of peaks and troughs, longitudinal waves have something different: compressions and rarefactions. A compression is just an area where all the particles get bunched up together. That's high pressure. And a rarefaction is where they all get spread apart. That's low pressure. The whole wave is just this constant cycle of squeeze and release, squeeze and release. And you know what? We can still measure its wavelength. For this kind of wave, it's the distance from the middle of one of those bunched up areas, a compression, to the middle of the next one. It's the exact same idea as measuring from peak to peak, just applied to a pressure wave. So we have these two waves that look totally different, right? An up and down wiggle versus a back and forth pulse. How on earth can we talk about them and compare them in the same way? Well, the answer is graphs. By plotting how pressure changes over a certain distance, we can take an invisible sound wave and turn it into a clear visual graph. And you know what's cool? Suddenly, it looks just like a transverse wave. This means we can use the same language and the same tools to analyze both of them. We generally use two main types of graphs. The first one is a displacement distance graph. I want you to think of this like a photograph. It's a snapshot of the entire wave at one single instant in time. This is what shows us its amplitude and its wavelength. The second one is a displacement time graph. This is more like a video that's zoomed in on just one single particle, and it tracks its movement up and down over a period of time. This graph is how we figure out the time it takes for one full wave cycle to happen. And from that time period, we get something absolutely crucial: frequency, which we measure in hertz. So, if a wave has a frequency of 50 hertz, what does that mean? It means 50 full cycles, 50 complete waves are passing by a specific point every single second. It's basically a measure of how fast the vibration is. So let's end on this thought. You're seeing this because of light waves and hearing it because of sound waves. We've got that covered. But what about the Wi-Fi signals, the radio broadcasts, the cell phone signals? The air all around you right now is like a bustling highway of invisible energy on the move. So what waves are you in the middle of right now?